I'm going to talk today about optimizing air sea flux observation strategy for the Southern Ocean. And this is really just revisiting a paper that we did a few years ago in conjunction with a postdoc, Yanju Wei, who led this study and who was based in Hobart for the project, but supported as a SOOS activity. So the starting point for this is really thinking about how sparsely observed the Southern Ocean really is for air sea heat fluxes. And the figure on the screen shows all of the locations where heat flux observations were collected in July from 2000 to 2004. And you can see there are a lot of dots, but they are all on the northern edge of the Southern Ocean. There are two big spots. I don't know, can you see my cursor? Maybe not.
I can see it.
Okay, so the SOOS mooring, which is run by Australia, and the star represents the OOI mooring, which was relatively briefly deployed by the US. And so those are the only two moorings that have been available in the Southern Ocean. And that obviously has really limited our available observations. Now, if you think about what governs changes in the Southern Ocean, Argo data show that the Southern Ocean is warming up. They show the global ocean is warming, but really all of the warming is happening in the Southern Ocean, as this Remick et al. Paper shows, where the only line, the ocean is divided into three regions, and we're looking at heat content change for over the period from 2005 to 2014. You can see the only real warming is happening in the region from 60 south to 20 south. If you translate that into an air sea heat flux, it implies a net heat flux on the order of about 0.5 watts per meter squared, which is tiny and very hard to measure. But model results attribute this warming definitely to air sea heat fluxes that are happening in the Southern Ocean. So even if it's hard to measure this, just to understand the mechanisms that are governing what's happening in the Southern Ocean, we'd obviously like to have a pretty good handle on heat fluxes and how they occur. In a broader context, I wanted to put this in the framework of the global observing system strategy. So Megan Cronin has led a SCORE working group called Observing Air Sea Interaction Strategy, OASIS, which has done a lot to really think about our community priorities for measuring air sea heat fluxes. And that translates into a series of grand ideas. Grand idea number one, to develop a globally distributed in situ air sea observing network. Grand idea number two, to have satellites optimized for air sea heat fluxes that help knit together the observations. And grand idea number three, to improve models and understanding of air sea interaction. And then, of course, to serve the data forward to stakeholders and to produce useful predictions that benefit all of us. So our focus today is really on the in situ observation part of this. And our challenge is asking where we should measure. If we've got this very sparse observing system and we are these tiny heat fluxes, but clearly we have some opportunities. And so you can imagine pursuing a multi-sensor strategy with some combination of in situ observation, satellites, and assimilation, as OASIS has suggested, and then thinking about where to put the in situ part of that. So this talk is going to explore one strategy for maximizing how well we explain the variance of air sea heat fluxes using a small set of moorings. But it's really just the beginning of a discussion for what an observing system might do. And to sort of think about what we might be looking for in air sea heat fluxes, I'm showing this work from a study that Veronica Tamzet led, where she compared the observations from the SOFS mooring and the OOI mooring, these lone two moorings in the Southern Ocean, over a period of time when they were both deployed from 2015 through to towards the end of 2018. And you can see where they overlap. They show very similar annual cycles. There's no reason they should be that similar. They're pretty far apart. But I think what really stands out in this is how much variability there is in the heat fluxes observed at these moorings. So the driving part of the heat flux, what really governs how much heat is stored or sequestered into the ocean interior, ends up being affected by a few very short-lived episodic events. You can see these spikes that are really enormous heat loss events that are just only a few per year. They're linked typically to strong winds from the south, wind coming off Antarctica, and that's driving deepening of the mixed layer, air-sea exchange, and everything that affects global ocean uptake of heat and carbon dioxide. So if we have an observing system, we'd sort of like to be able to capture something about these episodic, short-lived, high-frequency events. So in this context, then enter a discussion about how we might get more moorings out. And what happened is that on the Chinese side, Dake Chen came forward and said he thought that maybe China would be willing to fund a string of moorings. And he approached SOOS and said, where should we put them? So if we've got this multi-sensor strategy, where are we putting the moorings? So we've got this broad picture then. We have Argo, which is doing a great job inferring the long-term imbalances and changes in heat, salinity, even carbon dioxide with biogeochemical Argo in the upper ocean. But if we want to understand the mechanisms driving processes, flux moorings are invaluable. And we really want to understand the range of mechanisms that drive the variability, as well as providing in situ reference for satellite observations. So my strategy today is to look at this maximizing variance explained by a small set of moorings. The questions we can ask are, how do we optimize placement of moorings, which is what I'm going to do? And then the broader questions, how would sail drones or wave gliders enhance the sampling, which I'm not going to address today, but which I think could be part of a larger discussion. So I'm just going to talk through some of the figures that appear in the paper. First is the question, what do air-sea heat fluxes do in the Southern Ocean? And we obviously don't have great measurements, but we have reanalysis fluxes. This is JRA fluxes from 1979 to 2016. And you can see the mean, which shows a lot of patterns of spatial variability in the air-sea heat fluxes, and the standard deviation, which is substantial and a lot more than half a watt per meter squared, saying that there's a lot of variability in heat fluxes depending where you are. If we're going to look at them, a big part of the signal is an annual cycle. So if we look at these heat fluxes, you can see that there's an enormous annual cycle that's very repeatable. And so we don't really need to measure that to know what it's doing. We're just going to take that out of the signal and ask how well we can do with the residuals. So we've got the original signal in black, the harmonics in red, those are removed, and we're going to look at the residual and ask how well we can explain it. You can sort that residual signal into high frequency signal, which is the blue, and a low frequency signal, which is the red. And for this study, we took the high frequency signal as the baseline case. So we said, can we explain these rapid fluctuating heat flux events? So here we're looking at details of the fluxes, the high frequency signal on the top, the low frequency on the bottom, heat flux in the first column, buoyancy flux, so that includes evaporation precipitation effects converted into the same units, and the difference between them. And you can see that the difference is relatively small. Most of what we're looking at can be thought of in terms of the heat flux, and the buoyancy flux adds only a small amount to that. And so then you can ask, well, if we want to observe this, what can we do? So one strategy is to say, we've got this highly varying system. Let's just explain it in terms of empirical orthogonal functions. So we can take the heat flux, the high frequency part and the low frequency part, and I've dumped everything onto one slide for discussion purposes. So we can come back and talk about it later. But imagine taking that whole heat flux and splitting it into empirical orthogonal functions, into modes of variability. So we have the spatial pattern in the map and the time series that goes with it as line plots for the first three modes for the high frequency signal and the first three modes for the low frequency signal. And what you might suppose you could do would be to say, okay, let's find the major parts of variability. Look, they're sort of highs and lows here. And what if we put a mooring in each of those spots? We could really map out mode one very effectively. Of course, that would be terrible for mode two, which is orthogonal to it. But we laid that out as a potential observing system deployment strategy and said, okay, here's where you put the moorings. And this is showing several different scenarios. The black dots, imagine putting a mooring, a hypothetical mooring in each of the EOF1 high frequency extrema. So you really get a good sample of that high frequency mode. And then the cyan dots are just saying, okay, suppose we really wanted to get the Amundsen Sea low and the southern annular mode, where would you put moorings? And that puts them in a different set of places. We looked at trying to get EOF mode 2, which is in black stars, and EOF mode 3 in cyan stars. And you can see that this has a strategy of putting moorings all over the place. The purple dots show where we're currently placing moorings, or where the OOI mooring was and the SOPS mooring is, and they're not necessarily well aligned with any of these sites, but that's one framework. It doesn't really narrow down where we're sampling. And moreover, if our EOFs were really effective as EOFs, we'd be massively oversampling EOF1 if we put a mooring at the high in each of these EOF modes. So we might really want to say, how do we best sample the overall variance of the system by maybe capturing one mooring for mode 1 and one mooring to capture mode 2. And so we set out to try and test this problem in an iterative approach. And we said, okay, let's look at the variance in the entire Southern Ocean, the standard deviation of the high frequency variance. And let's suppose that I want to find a spot to put a mooring that is best correlated with everywhere else in the Southern Ocean, so that I can explain as much variance as possible. So we laid out an equation that looks like this, where we're trying to find the correlation between a reference site, R0, and all other sites where there could be a heat flux measured by reanalysis. So we position mooring number 1 at the spot that is best able to explain the variance in the entire system. And then we look at the portion of the overall variance that's explained by the mooring, which is, turns out not to be so high, and the correlation between that site and everywhere else. And you can see it has spots that are positively and negatively correlated. And then we can take that part of the signal out and go on and add another mooring. So we're going to assess the variance explained, remove the correlated signal, and repeat. We do that. Here's mooring number 2, which if mooring number 1 was here, mooring number 2 gets shifted about over by, I guess, 30 degrees. So it ends up being really nicely orthogonal. And it captures a different mode of variability that is, it represents a different part of the signal. So that's mooring number 2, and we could keep going. So we ended up identifying 6 mooring sites that are plotted in the paper. I think we even did a couple more than that in the final figure. And you can look at the correlation of those with the whole Southern Ocean. And you can see that mostly the heat flux is really well correlated in the neighborhood of the mooring and not so well correlated everywhere else. So we're not capturing the whole variability of the system, but we're at least measuring signals that are not heavily correlated with each other in this strategy. So here are then the 8 mooring positions that are identified in this system. And you can see from the red circle and the red star that we started with, we go through and put moorings in the Indian sector and more in the Pacific and the Atlantic sector. So what's interesting is, in fact, that position number 2, this guy, is approximately at the location of the now defunct OOI mooring. So that was not such a bad spot if you were trying to find one site that represented everywhere. But well, of course, we expect that there's a lot of synoptic weather and higher frequency signals that aren't even being resolved here that will lead to even greater differences. So, and then we said, okay, well, that was one cost function. We can think of this a whole bunch of other ways. So we have the high frequency signal I just showed you, the base case, but we looked at low frequency signals. And we also looked at where you'd go if you weren't interested in correlation. You just wanted to find the largest local variance once you took out a signal. So So we did that in our base case. We looked just south of 40 South. We looked at a sample where we did no area weighting, so the geography was weighted slightly differently. We looked at a case where we assumed that we had the OOI and soft mooring permanently deployed in their baseline locations, and we looked at a different heat flux product, the ERA reanalysis product. And you can see that each of these leads to slightly different mooring positions. ERA is fairly similar to the base case with JRA, but other scenarios end up with quite a few differences, and that ultimately leads us to maybe not have really answered the question, but where do you put your 6 new moorings? But it at least gives us a recipe for saying, if you're going to put out moorings next week, how might you make a decision about where to put them? So you can develop, turn the crank with your latest updated heat flux product and decide on a bunch of locations. And then if you can get the ship time to get there, you're set. So how well does this work? Well, if you look at, again, back to our base case of high frequency heat flux, here's the overall standard deviation, here's the reconstructed standard deviation, and here's the difference. And you can see we've left a lot on the table. In total, we're explaining about a quarter of the variance. And the best we could hope to do with the first 8 EOFs, perfect fit for the whole spatial structure of those EOFs would be about 37%. So it's not so bad, but there's a lot of variability. It's just hard to capture. So I'm going to summarize here and we'll have some time for discussion. Obviously, in situ flux observations are a really key component of the Global Ocean Observing System, OASIS, of the Southern Ocean flux observations. And so in that context, we set out to develop a framework for configuring mooring arrays. We've optimized positioning for 8 mooring sites designed to explain the largest fraction of net heat flux variance poleward of 20 south. And as I said, the 8 moorings explain about 25% of the high pass filtered variance. If we use the low pass filtered variance, we'd do a little better. There's more spatial structure. We could explain maybe 45%, so still under half. And then there are a bunch of open questions, how do we optimize flux measurements if we really want to look at what happens across narrow frontal features like the ACC frontal features? And as I said at the beginning, how can sail drones or wave gliders or other types of instrumentation that might move around help with this overall scenario? So I am going to stop there. I'm happy to take questions and talk.